Hey everyone! Welcome back to our deep learning series. I'm super excited about today's episode because we're diving into some of the most fascinating and advanced topics in deep learning. We'll explore powerful architectures like RNNs, LSTMs, and GANs, uncover the secrets of transfer learning and fine-tuning, demystify autoencoders and dimensionality reduction, get our hands dirty with a practical deep learning project, and finally, delve into attention mechanisms and transformers. Trust me, you don't want to miss this. So, let's jump right in. Deep learning architectures, RNNs, LSTMs, GANs. Recurrent neural networks, RNNs. Imagine you're reading a novel. Each sentence builds on the previous ones, right? Recurrent neural networks, or RNNs, work similarly. They're designed to handle sequence data, which is data where the order matters, just like sentences in a book. RNNs have loops that allow information to persist, making them perfect for tasks like predicting the next word in a sentence or forecasting stock prices. But here's the catch: RNNs can struggle with remembering long-term dependencies due to the vanishing gradient problem. It's like trying to recall a detail from a chapter you read weeks ago. Despite this, RNNs have paved the way for more advanced models that can handle these challenges better. Long short-term memory networks, LSTMs. Enter long short-term memory networks, or LSTMs. These are like the supercharged version of RNNs. LSTMs can remember information for long periods, thanks to their unique structure featuring a cell state and 3 types of gates: input, forget, and output gates. Think of these gates as traffic lights controlling the flow of information. Because of this, LSTMs excel in tasks where context is king, such as speech recognition and language translation. They can keep track of the storyline across many pages of our metaphorical novel, making them indispensable in the world of deep learning. Generative Adversarial Networks, GANs. Now, let's talk about something truly exciting: Generative Adversarial Networks, or GANs. Imagine 2 artists in a friendly competition. One creates stunning forgeries while the other tries to identify the fakes. This is the essence of GANs, where a generator creates fake data, and a discriminator tries to tell it apart from real data. This adversarial process leads to incredibly realistic outputs, from photorealistic images to lifelike videos. GANs have even been used to create art that's indistinguishable from human-made pieces. They're a testament to the creative potential of AI, and they're pushing the boundaries of what's possible in deep learning. Transfer learning and fine-tuning. Transfer learning. Picture this: you've spent years mastering a skill, like playing the piano. Now, you want to learn the guitar. Because you already understand music theory, your learning curve is much shorter. That's the idea behind transfer learning. It involves taking a pre-trained model, one that's already learned from a massive dataset, and applying it to a new but related problem. For example, a model trained on millions of images can be fine-tuned to classify medical images with fewer data. Transfer learning saves time and resources, making it a powerful tool when you have limited data for your specific task. Fine-tuning. Fine-tuning is like adding those finishing touches to a painting. After transferring the broad strokes from the pre-trained model, you make small adjustments to better fit the new task. This involves unfreezing some of the model's layers and retraining them on your specific data. By fine-tuning, you can leverage the vast knowledge the model has already acquired and adapt it to your unique needs. It's a critical step in transfer learning that enhances the model's performance and accuracy for your specific application. Autoencoders and dimensionality reduction. Autoencoders. Let's dive into the world of autoencoders. Imagine compressing a high-resolution image into a tiny thumbnail and then trying to reconstruct the original image from it. Autoencoders do something similar. They consist of an encoder that compresses the input data into a lower dimensional representation and a decoder that reconstructs the original data from this compressed form. Autoencoders are incredibly useful for tasks like noise reduction and feature extraction. They learn to capture the most important features of the data, which is why they're often used for dimensionality reduction, simplifying complex data while preserving its essential information. Dimensionality reduction. Speaking of dimensionality reduction, it's all about simplifying your data without losing what makes it valuable. Techniques like principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, are popular methods for this. They help visualize high-dimensional data and improve machine learning models by reducing noise and redundancy. Autoencoders also excel in this area by learning a compact representation of the data, making it easier to work with while retaining its core features. Hands-on, deep learning project. Alright, let's roll up our sleeves and get hands-on with a deep learning project. We'll build an image classification model using transfer learning and fine-tuning. Here's a step-by-step guide. 1. Dataset. We'll use the CIFAR10 dataset, which contains images of 10 different classes. 2. Pre-trained model. Load a pre-trained model like VGG16 or ResNet50. 3. Transfer learning. Freeze the initial layers of the pre-trained model. 4. Fine-tuning. Unfreeze the top layers and train them on the new dataset. 5. Evaluation. Evaluate the model's performance on the test set. This project will give you practical experience with advanced deep learning techniques, showing you how to leverage pre-trained models and fine-tune them for your specific tasks. Attention mechanisms and transformers. Attention mechanisms. Have you ever been in a conversation where you need to pay close attention to understand the context? Attention mechanisms in deep learning work similarly. They allow models to focus on specific parts of the input sequence, enhancing their ability to capture dependencies and relationships. This has transformed tasks like machine translation, where the model needs to align words in different languages accurately. Attention mechanisms enable models to weigh the importance of different parts of the input, leading to better performance in understanding and generating human language. Transformers. Finally, let's talk about transformers. Unlike RNNs that process sequences step by step, transformers handle the entire input sequence simultaneously. This allows for parallelization, speeding up the training process significantly. Transformers use self-attention to weigh the importance of different parts of the input sequence, leading to superior performance in various tasks. Transformers have revolutionized natural language processing, NLP, with models like BERT and GPT, achieving state-of-the-art results in language translation, text generation, and sentiment analysis. They're also being applied to other domains like image processing and reinforcement learning, showcasing their versatility and power. Conclusion. Wow, we've covered a lot in this episode. From the intricate workings of RNNs, LSTMs, and GANs, to the efficiency of transfer learning and fine-tuning, the magic of autoencoders and dimensionality reduction, and the game-changing capabilities of attention mechanisms and transformers. Each of these topics represents a significant advancement in deep learning. If you found this video helpful, please give it a thumbs up. Don't forget to subscribe to our channel and hit the bell icon so you never miss an update. Your support helps us create more content like this. Thanks for watching, and I'll see you in the next episode.